All right, welcome back to the deep dive. So our mission, as always, is to take your sources and your research, and we distill it. We cut through the jargon to get to what you really need to know. Today, we're getting into the foundations of truly efficient code. Not just code that works, but code that, really scales. This is for you, the learner, who wants that shortcut to understanding the hidden mechanics behind every loop you write.
Yeah, I think today we're really bridging a gap between, this abstract theory-like classical design patterns and some really practical immediate performance gains. We're going to pull back the curtain on the mechanism that lets your code handle huge amounts of data without maxing out your CPU or just eating all your memory. If you've ever watched an application just choke on a big file, this deep dive is basically the blueprint for how to avoid that.
Okay, let's unpack this then. Let's maybe start with that big idea, a design pattern. We know it's a reusable solution, but let's focus on the why. Why do we even need them?
Absolutely. And we don't need to get bogged down in, textbook definitions. A pattern is there to give your code structural integrity. I mean, think about architecture. When an engineer builds a bridge, they're not inventing physics from scratch every single time. They use established principles.
Right, for things like load distribution, stress tolerance.
Exactly. Design patterns are that same kind of formal rigor, but for software.
So the iterator pattern, that's the one that deals with this structural problem of managing data sequences, right? It's about how you move through data.
Precisely. Yeah. It separates the how of your traversal from the what of your storage. So whether your data is in an array or a linked list, the iterator gives you one universal way to walk through it.
But I mean, this isn't all just theory, is it? There are real-world consequences. Even the best blueprints could fail. We talked about that historical example of the 1907 Quebec bridge collapse. It failed before it was even finished. And why? Because the design calculations just didn't account for the actual real whittled weight of the steel.
And that's such a perfect analogy for developers because just like that bridge, a simple list comprehension can bring your whole application crashing down if the data is too heavy for the RAM you have.
So the blueprint itself is fine, but you have to respect its limits.
You have to respect its capacity, absolutely.
So what's fascinating to me here is how the iterator pattern is. Like that specific structural column that stops our data sequences from buckling under a heavy load. Let's get into the mechanics of it.
Okay.
What's really happening when we write for item in sequence?
Well, the iterator pattern is so powerful because it's fundamentally simple. I mean, an iterator object, really, it just does three things. It gives you the next item, it tracks where it is, and it tells you when it's done.
So that simple for loop that, we all use every single day, it is not magic. It's actually a wrapper, kind of syntactic sugar around this underlying object.
That's it. That's the big reveal, right? In Python, it's all formalized through what they call the iterator protocol. For an object to be iterable, it needs a method called iter.
And that returns the iterator itself.
It returns the iterator object, and that object has to have the next method. So every time the loop runs, it's just calling next on that iterator.
Okay, so if the loop just keeps calling next, what stops it? How does it know it's at the end?
Right. It communicates with an exception. When it's out of items, it raises a stop iteration exception.
Ah, okay. And that's not an error we need to worry about.
Not at all. It's the formal expected signal. It's just the iterator telling the for loop, hey, my job is done. You can move on. It's communication, not a failure.
That makes sense. It's a formal protocol, and that gives us the structural integrity. Okay, so that's the engine room. Let's talk about the elegant dashboard. Comprehensions. They're built on this, right?
Completely, yeah. Comprehensions are just these beautiful syntactic shortcuts for doing all of that work. They are simple, they're readable, and they're incredibly expressive.
And their utility is it's off the charts. List comprehensions are so fundamental, whether you're building a huge service or, say, solving a puzzle on a site like Caddy's. They're just clean and fast.
And they're what we call eager. They immediately build the whole thing, the list, the set, the dictionary right away in memory.
But then there's that fourth one. The one that's, well, it's the game changer, right? The generator expression. This is where the real efficiency hack is.
Exactly. Now we're moving from give it to me now, that immediate gratification, to lazy evaluation. And this solves that memory problem we talked about.
So let's make this real for a second. Imagine you've got this, massive gigabyte-sized log file, and you need to find the average response time. If you use a list comprehension to read every line and process it, what happens?
And there it is. The Quebec bridge collapses again. You hit a memory wall. You're forcing the system to hold this huge intermediate list in RAM before you can even start your calculation.
This is where generator expressions come in.
They are the lifeline. They're like the anti-warehouse solution. Instead of building that huge container in memory, a generator expression is a reluctant producer. It creates a temporary data stream that only gives you the next value when you ask for it.
Lazy evaluation.
That is the definition of lazy evaluation. You only calculate what you need right when you need it.
So, syntactically, how does Python know? I mean, square brackets are a list, curly braces are a set. What's the signal for be lazy?
It's the parentheses, the curved brackets.
Wait, but hang on. Parentheses almost always mean tuple, right? Like 1, 2, 3 is a tuple. So why isn't this a tuple?
Yeah, and that's the brilliant, if slightly confusing part. The context is everything. The Python interpreter is smart. When it sees that for X in sequence logic inside the parentheses, it overrides the normal tuple rule. It knows your intent is to create a generator, and it's crucial to see this. If you just write, sure, you get an empty tuple, but if you write X for X in, you get an empty generator. The loop logic completely transforms the meaning. It's an efficiency override.
JIT delivery, just in time. I love that. It's a perfect analogy. Okay, so let's take this JIT idea and make it programmable. Let's talk generator functions.
For sure. Generator expressions are awesome for one-liners, but if you need more logic like if statements or complex loops, you need a generator function. They're special functions that return an iterator that just yields values.
Okay, so we know return ends a function, stops it cold. What's the key word here that makes all this magic happen, this whole pausing thing?
The magic keyword is yield, and it is fundamentally different from return.
Oh, so.
When a normal function hits return, its existence, its stack frame, all its local variables is just wiped out. It's gone. But when a generator function hits yield, that stack frame is preserved, the execution state is suspended, frozen in time, and it hands that one value back to whoever called it.
So they're literally resumable functions. When I call next on it again, it doesn't start over.
No, it picks up right where it left off, exactly on the line after the yield. This ability to suspend and resume is what lets you process, a terabyte of data one piece at a time without ever storing it all.
I often think of these as being similar to something like the built-in range class.
Yeah.
They both let you handle huge sequences without storing them. Is that a fair comparison?
Conceptually, it's an excellent comparison. They both share that core benefit. Efficiency through non-storage.
Yeah.
Range of 1 billion doesn't create 1 billion integers,
Yeah.
but technically, and this is a really interesting detail range, is actually so highly optimized it kind of breaks the rules. It doesn't implement next directly. It's a perfect example of how sometimes, for maximum performance, you have to bypass a standard pattern. But if we connect this to the bigger picture, understanding the difference between yield's temporary pause and return's final stop it's just key to writing scalable code.
Wow, okay. That was a fantastic deep dive. So we started with these big architectural ideas, these design patterns, and learned that even the best blueprint can fail, like the Quebec bridge. Then we dissected the engine behind every for loop, the Iterator protocol, and learned the shortcuts, the comprehensions.
And we ended up with the real tools for scale. Generator expressions and generator functions all powered by lazy evaluation. I think the takeaway for you is knowing when to choose which tool an immediate list or a memory-saving on-demand stream.
And that brings up a final thought. Since we found out that something as basic as range has its own special, non-iterator logic for performance, here's something for you to explore. What other built-in Python objects designed for huge data streams, things like memory views or I/O objects, might also be using this kind of highly optimized non-standard logic? And what are the specific performance implications of that choice for your code? Something to mull over. That's it for this deep dive. We'll see you next time.